So, we are discussing about zinc, lambda max etc. 620 and 520 negative also you can determine, and then I showed you this curve zinc-on 10, 20, 30 ppm you can happily determine up to 30 ppm, but it is on the higher side. So, the lambda you can 1 ppm should be fairly good enough for your requirement for water monitoring. And then the least square feet is a very good straight line passing through the origin with about 45° slope, and R square value is 0.999, which means it is a very reliable method. Now, we will move on to another two parameters, that is determination of nitrate. So, I would like to tell you that of late nitrate has become a very important component in drinking water quality. It has assumed more importance, earlier it was not, but nowadays because of the effect of nitrate causing infant methemoglobinemia, that is a type of blue baby syndrome. Nitrate has been implicated in the disease of methemoglobinemia, and it has also been implicated in cancer and problems of digestive, circulatory and nervous systems. The problem is not because nitrate is there in more higher quantities, but the nitrate in our day to day life is becoming higher. So, the threat of nitrate in the drinking water is increasing day by day. For example, in normal river waters or surface waters or pond waters, well waters, you will not come across high quantities of nitrate, but because of the presence of other elements in drinking water like fluoride, chromite, chromium, arsenic etc., most of the Indian government is sanctioning reverse osmosis units all over India. Okay. So, the reverse osmosis units are intended for removing the toxic elements like fluoride and then arsenic etc., but the principle of reverse osmosis implicates the rejection of about 30 to 60% of water, which is known as reject water. Remaining 50 to 60% is permeate water, which is useful for drinking. So, the reverse osmosis works on the principle of essential diffusion through a membrane, and the permeate will be having very less concentration of the toxic metals, but the reject will have correspondingly increased anions and cations. So, if you get about 50% of drinking water as an RO permeate, remaining 50% you will have to waste. The problem is in the remaining 50% of the water, the concentration of the elements will increase several fold, and the importance of nitrate comes from this fact that the nitrate content quite often increases in the reject RO reject, which people are forced to utilize for their day to day purposes. Also, nitriding is an industrial process, and then all these effluents containing nitrate, nitrite etc., they all end up getting oxidized into nitrate, and the concentration of nitrate increases. It is also an industrial product coming from soaps and other things, other cosmetics, and the nitrate concentration keeps on increasing in the effluent water or surface water or the pond water, borewell water, etc. So, the concentration of nitrate normally should not exceed 40 ppm. In 90% of the cases, if you are using water directly for drinking, the concentration would be very less, maybe 2 ppm, 3 ppm, 5 ppm, it does not pose a threat. But wherever there is a treatment system involving the RO, reverse osmosis, nowadays you should remember that almost every household in India is having a home RO system, as well as in industrially we employ large quantities of RO systems for industrial purposes. So, it has been because of its implication in several diseases, the importance of determination of nitrate has increased several fold, and Bureau of Indian Standards prescribes a limit of about 40 ppm as nitrate, out of which 10 ppm should be as nitrate nitrogen. The other forms of nitrogen in drinking water would be nitrite nitrogen and ammoniacal nitrogen and several other types of nitrogen, but nitrate nitrogen should be less than 10 ppm as nitrate nitrogen, and 40 ppm of nitrate in drinking water is definitely harmful. You should not be drinking. So, there is a wonderful method for the determination of chromium, for the determination of nitrate. The reagent is chromotropic acid. Chromotropic acid is nothing but the sodium salt of 1,8-dihydroxy 3,6-naphthalene disulfonate, that is a organic reagent and almost specific for nitrate. The nitrate reacts with this reagent in sulfuric acid medium to give a yellow color complex. The intensity of the color, if it is yellow color, without my telling, you should remember that it should be around 400 to 410 nanometers should be the lambda max. So, we look at the first slide of this, which is the which sort of presents in before you all the ideas that I have presented for this nitrate introduction, that should serve as introduction, and this is the structure of chromotropic acid. You can see that it is a naphthalene ring and then both are aromatic and with 2 SO3H groups and 2 OH groups. The complexation with nitrate will happen with the removal of water from these OH groups. So, there will be some sort of ring closure and the color will be shifted to the bathochromic side, and that is how the determination of nitrate is completed using the spectrophotometric finish. Now, the other things become very simple because we have sort of standardized that we prepare up to 100 ppm of sodium nitrate solution. We prepare stock using 0.137 gram of sodium nitrate. You have to remember that most of the sodium salts are soluble in water. So, there are no specific instructions for you to dissolve sodium nitrate. Same thing is true with respect to dilution. Simply dilute 10 times, you will end up with sodium nitrate. And chromotropic acid, you have to prepare 0.1%, it is available across the shelf. But only problem is you have to dissolve the chromotropic acid in concentrated sulfuric acid, and you have to dilute also with concentrated sulfuric acid. This is somewhat hazardous. I think most of you are aware that concentrated sulfuric acid, you should be very careful in handling, and wherever it is a very highly corrosive liquid, and it is part of the hazardous nature of the chemical laboratory that if you want to determine chromotropic acid, there is spectrophotometrically you have to live with the fact that you have to use concentrated sulfuric acid with all the associated precautions. Okay. Now, you need complexing agent, especially in this area for the determination of nitrate. For that you have to use urea as well as some sodium sulphite in about 50 ml of deionized water and dilute up to 100 ml. Sometimes what happens is the sodium sulphite is a reducing agent. So, we have to prepare about standard nitrate solutions using 0.1 to 0.6 ml of 100 ppm into different flasks, add 1 drop of sulphite urea solution to it and pipette about 2.4, 2.3 etc. to make them 10 ml. Okay. So, deionized water to convert everything into 2.5 ml. So, then you have to add this antimony solution followed by 1 ml of chromotropic acid solution, and after about 45 minutes the color develops and you have to measure the absorbance of each solution at 410 nanometers against the prepared blank. This is a very simple procedure. I do not have to read you the procedure, but still for the sake of record I do make such concessions as has been the procedure so far. So, we can prepare a calibration curve of the absorbance versus concentration of nitrate, and the cookbook recommended volume is 1 ml and the cookbook value for 50 microgram in 10 ml, that is 5 ppm, that gives you an absorbance of about 0.202 plus or minus 0.01, that is 0.19 to 0.21 you should be able to get without any problem with ordinary spectrophotometers, whether it is prism or grating or even a simple colorimeter, because 410 is usually covered in most of the spectrophotometer colorimeters also. There are several pocket colorimeters available, and in the last class I will talk to you about portable and other small devices that can dedicated devices that can be used for such things. So, there is this is the absorption spectra of nitrate, and that is the absorbance varies, and you can see that lambda max is around 410. It is not very broad molecular peak. So, you should have a fairly good spectrophotometer for the measurement, even though colorimeters have been used for such purpose. But when you use a colorimeter for measurement of nitrate in chromotropic acid, you need an interference filter that will give you more accurate value than the normal color glass filter, etc. So, that is the only thing I wanted to tell you with respect to this absorption spectra, and this is the calibration curve for chromotropic acid. You can see that it is a fairly good fit, the up to 60 ppm, and the absorbance what I am presenting here does not exceed 0.4. We have found that above this absorption the curve will bend towards x axis. So, to maintain the linearity we have fixed it up to 60 ppm, that is 60 micrograms in 10 ml, that is 6 ppm, and you can see that the linearity is quite good, 0.995, even though it is not the least square fit number 0.995 is not very good. We normally say 0.997 to 999 is a very good curve, but it is acceptable as far as we are concerned within plus or minus 2-3 micrograms error. I think this should be quite eminently suitable for the determination of nitrate in the by the chromotropic acid method. Okay. So, this brings me to I would also like to add the effect of nitrate on the other elements. For example, the interference in nitrate you can expect quite a lot. So, for example, anions you may not, but definitely some of the metal ions you can expect. For example, fluoride does not interfere up to 200 ppm, and then chloride does not interfere up to 200 ppm. We have tested most of them for 200 ppm, because even in soils etc., you will not come across higher concentrations. Then manganese does not interfere, magnesium does not interfere, nitrite does not interfere, chloride does not interfere, ammonium, iron, copper, all these things are up to 200 ppm will not interfere. Among the cations, iron, cadmium, vanadium, antimony, zinc, sulphide, cobalt, nickel, arsenic and mercury, they do not interfere up to 200 ppm. That means this procedure is essentially specific for nitrate. So, without any complications in the procedure, you can say that typically you can determine, go ahead and determine without much experience also, you will get fairly accurate values. If you want to determine in soil or drinking water or anything, it is essential for us, especially for the small children. Higher nitrate containing materials are slightly dangerous. So, this information should help you how to determine the nitrate using chromotropic acid method, one of the best methods I have ever come across, and typically a reliable method. That is all I can tell you at this stage. Now, the next element on my list is chromium. So, again I would like to tell you that chromium is a very celebrated element as far as toxicity is concerned. We know that the chromium is industrially a very important element, very widely distributed in the nature. So, in the soil also it is there in fairly decent quantities, but most of the chromium in the soil is not available to us as a labile compound. That means, whenever it rains or something like that, chromium salts do not dissolve and then flow into the surface waters. But chromium is a very important industrial metal. It is required for the production of stainless steel vessels, stainless steel reactors, and then chromium plating is one of the most well known industrial method for the determination of bright surfaces which are neutral to several chemicals, and they are also sort of corrosion resistant elements, chromium. So, chromium coating does not result in serious corrosion, but on the flip side, chromium is a carcinogenic element, especially hexavalent chromium, that is chromium 6 plus is carcinogenic. Chromium 3 is not carcinogenic, that is trivalent chromium. Unfortunately, in the environment, under suitable circumstances, chromium 3 gets converted into chromium 6, gets oxidized into chromium 6. Therefore, there is a limit for the determination of chromium in the effluent. The normal effluent concentration is about 0.05 ppm. So, the determination of chromium in industrial effluents is a very important process. 90% of all governments in India and other countries put a restriction on the concentration of chromium in the effluents, in the industrial effluents, and drinking water also we do not want a very high concentration of chromium. So, with this introduction I would like to take you to the analytical aspects of chromium. So, the diphenyl carbazide method is a very celebrated method for the determination of hexavalent chromium. Diphenyl carbazide in acid medium reacts to produce a red violet compound. It is an inner complex. This is not there in the text, but for your information, I want you to study the structure of chromium and diphenyl carbazide complex. Fiegel and other books usually describe the preparation of diphenyl carbazide complex and structural studies also. And in the diphenyl carbazide method, chromium 6 reacts with diphenyl carbazide in acid medium to produce a red violet complex. The absorbency is around 545 nanometers, that is somewhat violet in color, slightly bluish violet in color. This is the diphenyl carbazide. You can see that it is a diaromatic ring structure with NH, NHO, NH, NH this thing. Diphenyl carbazone is also one of the similar structures, and the reagents, what you need is basically chromium solution and diphenyl carbazide solution. You need some sort of buffer to prepare the final working solution to around pH 4. So, stock solution, I am recommending you handle very less chromium even in your day to day life. So, we recommend 100 ppm is more than enough for your stock solution. You have to dissolve 0.0283 gram of potassium dioxide in deionized water, very highly soluble in water. And several the color of the complex, even 100 ppm would be quite dark yellow color. In fact, the several industrial areas in and around Bangalore, whenever you dig a well around borewell, even up to 150-160 degree feet, you get chromium containing water up to 160 ppm, 150 to 160 range you will get. So, that is all dark yellow color in this thing, but for our studies chromium we can prepare up to 100 ppm. Then we can prepare this standard working chromium, that is 5 ppm, that should be allowed, that should be okay. You dilute 5 ml, that is about 20 times dilution, and hydrochloric acid we need about 100 ml. So, one normal should be more than enough. The procedure is to transfer up to 5 ppm to 10 ml volumetric flask and add 2 ml of hydrochloric acid, followed by 0.5 ml of diphenyl carbazide solution to each. The diphenyl carbazide you have to dissolve it in methanol. Normally it is not easy to prepare dissolve in any water. So, certain amount of methanol has to be incorporated up to 50% for the solution. So, 0.5 ml of 1% should be more than enough diphenyl carbazide, and allow it for about some 10 minutes, measure the absorbance at 545 nanometers. Then you can prepare a calibration curve followed by all other parameters that we usually normally look at. So, recommended sample volume is 2 ml, a cookbook value of about 10 microgram of chromium in 10 ml should give you an absorbance of about 0.383 plus or minus 0.01 absorbance. Very reliable method and very celebrated method. Most of the textbooks do describe this experiment as a standard textbook as well as for practicals. Many MSc students etc. engineers use this method very routinely, and this value has been obtained in number of occasions by all researchers, and the lambda max, here I am showing you the lambda max of these two solutions. So, the bottom one, what you see here is the reagent blank, and the top one is the absorption spectra for diphenyl carbazide chromium complex. You can see that around 540 the curve is fairly broad, plus or minus 2-3 nanometers does not make much difference to the sensitivity of the method. So, basically the method is applicable to several industrial samples, and the method can be adopted for routine analysis. Okay. So, this is the calibration curve. You can see that the linearity is up to 2 ppm. So, if my absorbance value is about 0.4 with respect to at 0.5 ppm, 0.04 would be our drinking water level testing. So, 0.05 ppm should give us 0.04 absorbance, which is quite high with respect to drinking water. But what we can do is we can take a higher sample, and instead of 1 ml we can take 5 ml and then bring it to decent level for measurement between 0.2 and 0.8. That is the proper, that is the aim of all experiments with respect to relative concentration error. So, that completes our discussion about aluminum. I will give you a small introduction regarding the determination of aluminum, and I have not informed you about the interference of chromium. Before I proceed to aluminum, I would like to talk to you about the interference of chromium, other elements in chromium. In general, we are normally worried about the anions, especially whenever we are using azide and other chemicals for spectrophotometry. We normally worry about the anions. Among the anions, iodide, bromide do not interfere. Iodide and bromide do not interfere with up to 100 ppm. Remember, for our cookbook value, we are preparing 1 ppm. So, 100 times this concentration will, if the iodide is more, it will not interfere. And the same thing is true with respect to bromide. And then what about chloride? I would like to ask you such questions, especially in the examination, because I have not been, I do not normally tell about the interference of chloride in this method, but you have to think about the procedure, because if I am using one normal HCl for the adjustment of pH or around pH 0.2 or point something or 2 normal HCl, obviously it means that chloride will not interfere. Same thing would be true of sulphate also. So, if the acidity is high, we would be either using chloride or sulphate, but if it is nitrate, I may be slightly worried, because nitrate nitric acid has got an oxidizing property. So, nitric acid may cause some amount of interference by destroying the diphenyl carbazide reagent. So, such tricks we normally employ in most of the examinations, but if you remember the procedure, if you look at the procedure carefully, you can answer many of these questions without any problem. So, in this method chloride does not interfere, sulphate does not interfere, nitrate does not interfere, that is nitric acid will not interfere, and cobalt, magnesium and iron and copper. Iron up to 100 ppm will not interfere, but copper reduces the absorbance by about 0.297, that is instead of 0.38 you are getting about 0.29. That means there is certain amount of interference whenever there is copper. So, we try to reduce this by decreasing the concentration of copper to see how long, at what level the interference of copper becomes negligible. Then what we do is we reduce it to 10 ppm, 50 ppm like that until we reach the equivalent value. So, if I say that up to 5 ppm, if the absorbance is within plus or minus 0.03 nanometers, it is not interfering. So, 10% we can make it. So, up to 5 ppm we do not have any problem with respect to this thing, but unfortunately copper even in 5 ppm it gives you an absorbance of 0.33 instead of 0.38, 5 ppm level, that is equivalent level. So, we can draw two conclusions from this. One is copper definitely interferes, but if the interference of copper is with the formation of another compound, another complex, then the another complex we, by increasing the concentration of the reagent, we may be able to overcome the interference. But if the concentration is if the copper is having a preferential interaction with diphenyl carbazide, preventing the formation of chromium complex, then we should definitely call it interference. But if it is structured, it can be reproducible. Copper is one such case where 5 ppm of 5 ppm will definitely give lower result, but it does not interfere in the, whenever you have 5 ppm it will give the same result. That means the interference of copper can be factored into the calibration of chromium. So, this point I wanted to convey to you regarding the interference of this, and then I also wanted to talk to you about triton, and triton is again a serious interferent, because up to 100 ppm it gives you very less absorbance, more than 10% change, but 10 ppm it is same problem, but around 5 ppm I do not have much problem. Fortunately, in most of our river waters the absorbance is always lower in the concentration of triton X anhydride in our river water is less than 5 ppm. So, but at the same time it is important for us to look at the concentration of chromium, concentration of triton X anhydride for the determination of chromium. So, I want to make a statement here that up to 5 ppm we do not have any problem if we have Triton in the reverse surface waters, Triton X100, that is a non-ionic surfactant, Triton X100. So, aluminum we do not have any problem, up to 100 ppm we do not have any interference. So, the idea is you can determine fairly confidently if you know the matrix components of the chromium effluent. So, drinking water definitely 0.05 is the limit, we do not have a choice, we have to go determine the chromium content. So, this is the, I think I have already covered this aspect, lambda max etc., and then this is also there, I have already discussed this. Now, in the next class what I would like to do is discuss the determination of aluminum and another 1 or 2 elements which I feel are important for you if you wish to pursue a career in spectrophotometry or analytical science. So, thank you very much. We will continue our class in the next meeting. So, have a nice day.